Welcome. We have been till now mainly discussing things within the solar system, and our discussion of the stars has largely concerned with the sun, though the equations that we developed can be applied to all stars. Today, let us start off by discussing how distances outside the solar system are measured. The most direct method for measuring distances outside the solar system is through parallax. We are quite familiar with the phenomenon of parallax. When we look at an object, its angular position changes when we move, and if you look at two objects at different distances, then the change in the angle is more for the closer object, it is less for the further object. So, if there are two objects at different distances and if you move, you will find a relative motion between these two objects. This is the basic idea in the measurement of parallax distances. Any observer in the earth is moving around the sun, and the radius of this circular motion, nearly circular motion, is quite well determined. That is one astronomical unit. So, this is the sun, and let us say that this is the earth. They are obviously not drawn to scale, and the earth goes around the sun once every year. And the radius of this circular orbit is very well known, it is one astronomical unit. Now, if you look from the earth, if you observe a star, let us say that this is a star, we observe this star from the earth, and this is the angular position of the star when the earth is at this position. Then the angular position of the star, same star, would have changed when 6 months later. Now, the question is, how does one measure this change? One needs a reference point. For a reference, we consider very distant stars, very distant objects. So, if I have a very distant object, imagine a very distant object be much beyond the size of this screen or the size of this paper where I am drawing. So, just imagine such an object, and that object, the angle at which that object would appear would the change in that angle would be imperceptible, much smaller than the change in a nearby object. Okay, so, we could measure this change in angle with reference to a distant object whose angle does not change. Okay. And an object, this is how the distances for nearby objects beyond the solar system can be measured. These distances are referred to as parallax distances, and this gives us the most direct estimate of distances beyond the solar system. Okay. And the unit of distances beyond the solar system is based on this. So, the unit of distance beyond the solar system is a parsec, which is denoted by 1 pc per sec, and it is the distance where if I place a star here at this distance, this parallax angle would be 1 arc second. So, the parallax angle between this position and this position would be 1 arc second, or the entire parallax angle at a 6 months interval would be 2 arc seconds. Okay. So, a distance where if I place a star in 6 months interval, so I have to wait for 6 months and again measure the angular position of the star. If it has changed by 2 arc seconds, then I would know that this angle is 1 arc second. So, 1 parsec is this distance, and we can estimate, we can see how much, calculate how much it is. It is 1 astronom. So, this 1 astronomical unit is 1 parsec, the radius, this into the angle. This angle is the same as this angle. So, 1 astronomical unit, the radius here is 1 parsec into this angle, or 1 parsec is 1 astronomical unit divided by 1 arc second, and you have to convert this into meters, you have to convert this into radians. So, I leave this as an exercise for you, a very rather straightforward exercise. If you do it, you will find that this comes out to be 3.09 into 10 to the power 16 meters. Okay. So, this is 1 parsec, this is 1 parsec, that is the distance scale outside the solar system. So, within the galaxy, the stars that we see, we shall be talking about distances in parsecs, kiloparsecs, etc. Okay. So, this is the first thing. Next, let us consider the observations of stars or other astronomical objects. The quantity that we shall start with this quantity, the flux density. F nu, which we are familiar with already. F nu tells us the energy coming per unit time interval. So, that is per unit. So, flux density is essentially, if I place a detector 1 meter square, the energy coming there per unit time interval in the frequency range d nu. Okay. So, this into delta nu tells me the energy coming per unit, per meter square, the flux of energy in 1 second. Okay. So, F nu has dimension watts per meter square per hertz. We have already discussed how to describe radiation, or alternatively we could use F lambda, which is defined so that this into delta lambda tells us the amount of energy coming per unit area per second. Okay. So, F lambda has dimensions watts per meter square per meter. So, this we shall refer to as flux density. The quantity that is measured in any astronomical observation, suppose I am looking at a star or a galaxy through a telescope, the quantity that is measured in any astronomical observation is the flux, which is the flux density f lambda into the sensitivity of the observation into d lambda, and the sensitivity of my observation S lambda incorporates the effect of the atmosphere that we are looking through, after all every observation from the earth is through the atmosphere, and the atmosphere may not allow all wavelengths to pass through equally. Then it also includes the telescope. The telescope may not respond equally to all wavelengths. So, that is there in the sensitivity, and also the detector, the final instrument that detects the amount of measures the amount of radiation also may not have an equal wavelength response, and the flux that is measured finally is an integral of the flux density over the wavelength with the sensitivity, and the sensitivity incorporates all of these effects.
So,
yeah.
In the new unit, shouldn't there be a per second also?
F, this is watts already per second. Okay, so this is already there, energy per second, that is watts. Okay. So, this is the quantity that is measured in any astronomical observation of a source, the flux. Right. Now, in astronomy, it is standard procedure, particularly in optical astronomy, to quantify the flux, the brightness of an object using units which are referred to as apparent magnitudes. These units, they were actually inherited from the ancient astronomers. The ancient Greek astronomers, they classified the stars that they could see visually, and the brightest stars were given a magnitude 1. So, the brightest stars that they could see were of the first, had a magnitude 1, and then the ones which appeared to be roughly half as faint, something like that, they were given fainter stars, were given the magnitude 2, and the faintest stars that are visible to the naked eye these have a magnitude 6, that is the faintest, which are visible to the naked eye. So, this was done by the ancient Greeks. They classified the stars and they gave this associated these kind of numbers, this kind of a scheme. Okay. Now, later people discovered that the eye actually had a logarithmic response. The response of the eye is not linear. if you have a linear response, the dynamical range, that is the brightest and the faintest object that you can see, will not be very far apart. But if you have a logarithmic response, your dynamical range becomes much more. Okay. So, the human eye has a logarithmic response. Okay. So, the eye what do we mean by this? What we mean is that if you have an object and you have another object, if you increase the flux by 2 times, it will not appear twice as bright to you. It will appear by a small, the difference will be relatively small. Okay. It is the ratio, the log of the ratio that you will see as the brightness, change in the brightness. Okay. And it was later found that these magnitudes are related to the flux by this relation. So, the apparent magnitude is related to the flux like this, minus 2.5 log 10 into the flux of the flux plus a constant. So, it was found later that the apparent magnitude, which were defined by magnitudes which were defined by the ancient Greek astronomers, were related to the flux, the measured fluxes like this. So, it is minus 2.5 log base 10 of the flux plus a constant. The constant sets the 0 point of the magnitude scale. Right. Now, so this is the definition of the apparent magnitude. Let us just try to see, get an appreciation for what it tells us. The first point that you have to note is the larger the magnitude, the fainter the star is. So, the larger the magnitude, the fainter the object is, the lower the flux. That is the first thing. Okay. Second, let me ask you a question. Suppose I have 2 sources and the magnitude of these 2 sources differ by 5. Okay. So, I have M1, the first source, and let us say M2 is the second source, the magnitude, apparent magnitude of the second source, and M2 is M1 plus 5. So, let me ask you, what is the relation between the flux of this source and the flux of this source? There are 2 sources, 1 and 2. Let us say that this has a flux F1 and this has a flux F2. The question is, what is the relation between the flux of the first source and the flux of the second source? There are 2 sources. So, this is quite straightforward. So, we can just subtract the M1 minus M2. So, just consider M1 minus M2, and if you consider M1 minus M2, what you have is minus 5 is equal to minus 2.5 log base 10, and you have the ratio of the 2 fluxes, right, F1 by F2. So, you want the log base 10 of the ratio of the fluxes to be 2, to be minus 2. Right, which essentially tells us that to be 2, right, this should be equal to 5. So, it tells us that f1 is equal to 100 f2, 100 times. So, a magnitude difference of 5 we see corresponds to the flux going down by a factor of 100, 100. So, this source is 100 times fainter than this source. To the eye, it would appear 5 times the 5 magnitudes lower in the brightness scale. Okay. So, this gives you an idea of the magnitude scale. So, magnitude different 5 indicates the flux has gone down by a factor of 100. Okay. Now, these magnitudes are measured in different bands. So, apparent magnitudes are measured in different bands. So, different bands refer to different parts of the spectrum. What this refers to is of the electromagnetic spectrum. So, in a single observation, it is possible to measure the okay. Before I go into this, I should first tell you that the measurements of flux, measuring the flux from a source is referred to as photometry. These kind of observations are referred to as photometry. Photometry. There is another kind of observation that is possible, where you measure the relative intensity of the light at different wavelengths. Such observations are called spectroscopy. There you are not interested in the magnitude of the flux, total flux coming, but you are interested in the relative contribution in different wavelengths, different parts of the spectra. Such observations are called spectroscopy. These observations are targeted at measuring the flux from a given source, and the flux is measured in a specified wavelength range, which is referred to as bands. So, each band refers to a different part of the electromagnetic spectrum, and the band is implemented through filters. So, you have filters corresponding to each band. So, the response of the filter is there in this sensitivity S lambda, which we had introduced earlier. So, if I am doing photometry in a certain band, I tell you the flux or the apparent magnitude in a certain band, then this, what we do is, you take in the telescope, at the end of the telescope, before you measure the flux, you put a filter. The filter will only allow light of a certain range of wavelengths to pass through. That is what the filter does. So, this is a particular band, and you can have different band systems. Okay. Each filter, so these are filters, each filter is specified. So, which the filter defines the band, and each filter is specified by telling the effective wavelength. So, this is the effective wavelength. What is the effective wavelength? Okay. So, the effective wavelength would be lambda effective Okay, this is the effective wavelength. This is the this gives you an idea at which wavelength the filter responds. So, you specify the effective wavelength and the full width at half maxima. full width at half maxima. What do we mean by this? You determine the position where you have the maxima or the filter has maximum response, then find out where it has half that value. The width of this function at that point is the full width at half maxima. So, these two numbers are typically provided to characterize the filter. If you really want to characterize it fully, then you have to give the whole function S lambda. For the filter along with everything else, okay, but the filter will finally determine the sensitivity. So, this is telling you the sensitivity of the filter here. What I am showing here is the sensitivity of the filter. Okay. So, this is a very commonly used band system of photometric bands. It is referred to as the UBV photometry. U stands for ultraviolet. So, let me discuss this. U is ultraviolet, B is blue, and V is visible. So, this is the standard, this is a very standard photometric band system, okay, which are referred to as the UBV bands. And this table here shows you the effective wavelength corresponding to each of these bands. So, there are three filters, one corresponding to U, one corresponding to B, one corresponding to V. So, when you do any optical observation, if you are using this UBV photometry scheme, the light, when you when you look at an astronomical source, you measure the flux of light through each of these three filters separately, and you convert them into the apparent magnitude. Okay. And this U filter allows light centered at 365 nanometers to pass through, and it has a full width at half maxima of 66 nanometers. Okay. Similarly, the blue band is given over here and the visual band is given over here. The full width at half maxima are also given. For reference, this table also shows the solar luminosity in these bands. So, if I look at the sun, how much energy does the sun emit in this particular band? Okay. So, in astronomy, it is very common practice to refer to the luminosity of astronomical sources in terms of the solar luminosity. So, when we are doing this for in the U band, this tells you the solar luminosity in the U band. This tells you the solar luminosity in the blue band, and this tells you the solar luminosity in the visual band. This is in units of 10 to the power 25 watts. Okay. This column I shall come to later. So, this is a very classic photometric scheme, the UBV photometry. Okay. There are band systems which extend much beyond all the way into the infrared. So, this table shows you the Sloan Digital Sky Survey. This is a very recently completed, actually I think it is nearly complete now, sky survey, the Sloan Digital Sky Survey. So, it shows you the photometric system that was used in the Sloan Digital Sky Survey. They have not used these UBV bands for any image in the sky, any astronomical source in the sky. This has surveyed the entire sky. Okay. Most of the sky, maybe not the entire sky, but most of the northern sky at least. And they have used this band system. So, they have measured the flux in these 5 bands, and note that the bands here extend from ultraviolet all the way into the infrared. The Z band and the I band, these are in infrared. Okay. So, there are a variety of possible band systems, and it is very important when you interpret astronomical observations that you know the band in which the observation was made, otherwise it is meaningless. So, if somebody tells you this is the flux coming from a source, somebody does photometry and tells you the flux or tells you the apparent magnitude, then you should know the band in which the photometric band system in which the observations were done. This is the first thing. Okay. The second point here is that the apparent magnitude in the U band, for example, will be referred to as mu. The apparent magnitude in the B band will be referred to as mb, and the apparent magnitude in the V band will be referred to as mv. Okay. Or it could be U, or you could refer to it as ub and v. Okay. So, there are different notations to refer to the apparent magnitude in different bands. Right. So, astronomical observations are quantified in this way. Now, the measured magnitude, it is quite obvious that this depends on the distance, because the flux we know depends on the distance, it falls as 1 by the distance squared. So, the measured magnitude also depends on the distance. Okay. But there is something called a color. Okay. So, one can define something called a color. And you can have different kinds of colors. So, you could have a U minus B color. So, what is the U minus B color? It is the difference in the apparent magnitude in the U band and the B band. So, U minus B is equal to minus 2.5 log the flux in the U band divided by the flux in the B band. Similarly, you could also have a B minus V color. This again will be the ratio of the flux in the blue band to the flux in the visual band. What do these colors tell us? Okay. So, the color gives us an estimate of what we actually mean by color in when we use the word color in daily parlance. So, when I refer to the color of any object, I am wearing a white t-shirt, okay, or this is a red pen. It essentially refers to the relative contribution of the radiation in different wavelength bands, which is what the color quantifies. It is the relative contribution in different wavelength bands. Okay. So, the U minus B color will tell me the ratio of the light coming in this band, let us call this the U band, to the light, the flux of radiation in the blue band. This is wavelength and this is S lambda, okay, in two different parts of the wavelength spectrum. So, a larger U minus B so, suppose I have two sources, one which let us say 1 and 2, and 2 has a U minus B which is larger. Okay. So, for 2 U minus B is larger. What does it tell us? It tells us that the U minus B is larger implies that for 2 the blue flux is more than the ultraviolet flux relative to 1, because this is a larger value, this is a positive value, right. This is a positive value, this is more for the second source. Its being more tells us that for the second source this ratio is smaller, the blue has more flux than the ultraviolet. So, this implies that the source 2 is redder, right. Ultraviolet more, so it has more of the larger wavelength component, which is what we refer to as redder. So, for most astronomical sources, if you can think of the radiation as being a black body spectrum, the color then the color gives an estimate of the temperature. So, if you think of the source, if you can think of the radiation from the source in terms of the black body spectrum, which we have already discussed, then the color gives an estimate of the temperature, and the larger the color, say let us look at the U minus B color. So, if it is larger, it tells us that the flux in the blue band is more than the flux in the ultraviolet. So, we know that the black body spectrum, the peak shifts with the temperature, and the source gets redder as it gets cooler, it will get bluer as it gets hotter. Okay. So, the more energy will be there in this band for a hot source, and more energy will be there in this band for a cool, relatively cool source. So, this, if it is larger, it tells us that I am looking at a cooler source. Okay. So, the color gives an estimate of the temperature. The color information is independent of distance. Since it is a ratio of fluxes, its distance independent. Okay. And we shall be referring to color in the future, in the subsequent discussion, the color of the radiation from different sources. So, color refers to the difference in magnitudes or the log of the ratio of the fluxes at different bands. Okay. The next thing that we need to discuss is extinction, in the interstellar medium. So, extinction. Whenever we do any astronomical observation, we are looking at sources through the interstellar medium. So, the region between stars is not empty, it is filled with material, and we know that there is dust, particularly in the plane of our galaxy, there is dust. Okay. So, the dust absorbs light. This is what is referred to as by extinction. This is what we mean by extinction, interstellar extinction. Okay. So, dust grains, these are grains of particles there which are there between the stars, they absorb light. And if you measure the apparent magnitude of a distant object, of a star, it has been diminished, the flux has been diminished. In addition to the diminishing due to the distance, it also is diminished due to the extinction. Okay. The extinction also has another effect. This effect arises from the fact that dust preferentially absorbs smaller wavelengths. So, this process is more efficient in absorbing radiation of smaller wavelength as compared to that of larger wavelengths. Okay. This has to do with the size of the dust grains. So, if the dust grains have a size like this, it will be more efficient in absorbing radiation whose wavelength is smaller than this than it is in absorbing wavelength which is larger, and it will be wavelengths which are much larger than this will just pass through. They will not even notice that the dust is there. So, dust is very effective in absorbing high frequency or small wavelength light. It does not affect the redder light as much. Okay, it does affect it. So, what dust will do is it also causes reddening. It will make the radiation to appear redder. So, when you are looking at astronomical sources through dust, they will appear redder, then the radiation gets reddened than what it relative to what it started out with. Okay. And this is then noticeable in the colors. So, the color gets redder. So, color increases essentially. So, not only does the magnitude increase, but the color also increases, it gets red. Okay. And if you have some idea about the spectrum of the source to start with, then one can construct combinations of color. Okay. So, one can look at combinations of the colors, and one can then explicitly find out work out how much absorption has taken place. One can from this one can work out the amount of extinction and reddening. By using combination of colors. Okay. So, let me remind you what the basic idea is again. The dust absorption is not uniform at all wavelengths. So, it appears the radiation, it causes the radiation to appear redder, and this can be used, this knowledge can be used to construct combinations of colors which allow you to determine from the observation how much extinction and reddening has really occurred. They both will occur together, okay. They do not occur separately, that is the main point. And using this you can actually work out how much of extinction has taken place and correct for it. Okay. So, this is a thing that one has to bear in mind. The next point is that of distance. So, the apparent magnitude allows us to quantify the apparent brightness of a source. Okay. Now, what about the effect of distance? Suppose I want to compare not the apparent brightness of a source. A source could appear bright because it is near, another source could appear faint because it is far away, but in reality the fainter source could intrinsically be brighter than the one that appears to be. So, the one that appears to be faint could intrinsically be brighter than the one that appears to be bright to us. Okay. So, we would like to have something which allows us to compare the intrinsic brightness of the sources. Okay. So, that is what is done by using the absolute magnitudes. So, let us consider a source at a distance d and from which we are measuring a flux f. Okay. Let us now ask the question that if the same source were placed at a distance capital D, what would be the flux f? Okay. It is quite obvious that f, the flux, scales inversely as the distance squared. So, this would be right. So, it would be proportional to the distances squared, the ratio of the distances squared into the flux when it were at a distance small d. Now, so let us now use this and ask the question, what if my source at a distance small d has an apparent magnitude small m. So, this has, let us say, an apparent magnitude m. What is the magnitude corresponding to this? So, all that we have to do is take log of both sides and multiply with minus 2.5, and the constant will cancel out, it will appear for both of them. So, it will cancel out. So, what we have is m is equal to (2.5), it will become 5 log So, this will be log of this into minus 2.5. So, log of this into, there should be a minus here, right. The minus, I have to take log and then multiply it with minus 2.5, that will give the magnitude corresponding to a distance capital D. So, similarly, I have to take log here and then that multiply with minus 2.5, which will give me minus 5. Okay. And this. So, this is it. Now, to compare the intrinsic brightness of sources, what we do is we place them at a distance d equal to 10 parsecs, and this is what is referred to as the absolute magnitude. Okay. We refer to this as the absolute magnitude. So, if you place the source at a distance, any source at a distance of 10 parsec, what is the apparent magnitude that it would have? That is what is referred to as the absolute magnitude. So, this is used to compare the intrinsic brightness of different sources, the intrinsic luminosity, and it is called the absolute magnitude. So, let us now go back to our band, the UBV photometry band. Okay. Now, before we do that, so that we can now go back and ask the question, what is the 0, what sets the 0 of the magnitude scale? Let us go back and now ask the question, what sets the 0 of the magnitude scale? The 0 of the magnitude scale is set. Where is the 0? For which source is the 0? Right? Unless you know that, you will never know how to convert the measured magnitude into a flux. So, the 0 is determined using a bright star called Vega. So, this has magnitude, apparent magnitude 0. This sets the 0 point of the magnitude scale. Having told you this, now let us go back to the table that we were looking at. Let us look at the table. Okay. Now, here the last column in this table tells us the absolute magnitude corresponding to the solar luminosity, the solar radiation. So, the sun has an absolute magnitude of 5.61 in the U band. What does it mean? It means that if the sun were kept at a distance of 10 parsecs and I then were to then measure the flux in the U band, the magnitude would be 5.61. Okay. So, you can use this also if you wish, because to convert any magnitude to units of the solar luminosity, right, or to convert it into units of watts, because here you see this solar luminosity is given in terms of watts. Okay. Finally, I have to mention that the difference between the apparent magnitude and the absolute magnitude gives an estimate of the distance. So, this distance should be in parsecs, right, d. So, if I know the apparent, if I can measure the apparent magnitude of an object, if I know its absolute magnitude, this gives an estimate of the distance to that object. This number is called the distance modulus. Okay. Now, there are two effects which need to be included in this. The first effect is the effect of extinction. So, for the same source, it could appear fainter due to extinction, right. This is telling us that it will appear fainter because of the distance, but it could also appear fainter due to extinction. Okay. So, if you know these two and you want to estimate the distance, then you have to correct for the fact that the source could be faint because of extinction also, right. So, you have to put in this extinction parameter A, and bear in mind that this extinction coefficient is extremely wavelength dependent. So, it would be different in different bands. This is the first thing. The second point, so this takes into account extinction. The second point is for a moving object. If we look at this moving object, then its light gets, the frequency gets shifted, and absolute magnitude refers to the flux in the rest frame of that object. The apparent magnitude refers to the flux measured by us. So, we are measuring, let us say, in the U band, and the object, let us say, is moving towards us. Then what we measure in the U band in the object's rest frame would actually be, could be in the blue band. Okay. So, one has to correct for this effect also, and one can in principle correct for this if you know the spectrum of the object, the spectral distribution, and this is corrected by introducing something called the K correction, which takes into account the fact that when you look at a particular band sitting here, it corresponds to a different band in the rest frame of the object. This refers to the flux measured by us, the apparent flux, apparent magnitude. This refers to the flux in the rest frame of the object. Okay, so, that is incorporated through the K correction. This is called the K correction, and it is important in cosmology where the sources are all redshifting away from us. So, one has to incorporate the K correction there. Okay. So, let me stop here. Let me remind you what we have discussed today. Today, we have discussed first the length scale measured by parallaxes, and I told you what a parsec means. Second, we discussed magnitudes, the system in which you measure the flux of astronomical sources, and I told you what a magnitude was. It is a logarithmic scale. The more the magnitude, higher the magnitude, the fainter the source. Let me stop today's discussion here.